For our last unit of the year, we're going to talk about surface area and volume of shapes. And we're going to take all we know about the shapes that we've studied and use that to find surface area and volume. Before we get into that, though, we have to go back and pick up one piece of information, and that's how do I find the area of just any regular polygon. So remember what the definition of regular polygon means. A regular polygon is any polygon with all the angles and all the sides being congruent. The cool part about regular polygons is that any regular polygon can be inscribed or basically fits inside of a circle. So we're going to take what we know about a circle to help us find the area of these polygons. So let's start with a regular hexagon where each side measures 8. You can see that I've already got it drawn inside of a circle for you. So each of these sides is 8 because that's what it means to be regular. Now you can do lots of different things to cut this shape. You could cut this into 2 triangles on the side and a rectangle in the middle and try and find the area of each of those 3 pieces. If you didn't want to do that, you could draw a diameter right here and you could say, oh, I have a trapezoid on the top and a trapezoid on the bottom, and you could try and find the area of both of those things, and you would be able to do that. If you wanted to do both and say, well, I've got 4 triangles and 2 rectangles, lots of different things you can do. The reason I'm not going to do that is because it's going to be very specific to the hexagon. What I'm going to do instead is think, if I just started at the center of my hexagon, which is also the center of the circle, and I just draw out to each of these points of the hexagon, basically cutting this like a circle into pieces of a pie. What I notice right away is this. All of those segments that I drew were radii, which means all of these segments are the same because they went to a point on the circle from the center of the circle. So looking at each of those triangles, they each have a side that measures a radius, and 8. Which means all of these triangles are congruent by side, side, side. And if they're all congruent triangles by side, 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 I only have to find one of these and then multiply by however many I have, which in this case I have 6 of them. So off to the side over here, I'm just going to draw one of those triangles, and I'm going to try and figure out what is the area of this triangle. The only piece of information I have so far is that the base of that triangle measures 8. I do know that it's isosceles, but I don't know that each of those sides measures 8 or 10 or 12 or whatever that may be. So I'm still a little stuck. Here's where the circle comes in. On the circle, if I draw a radius and another radius to create an angle, what I've done is created a central angle. Well, this central angle is the same angle in the triangle that I've redrawn over here. And a central angle always measures the exact amount of the intercepted arc. So if I can find that arc, I can find that angle, and then I'll be able to use that angle to help me find the missing sides of my triangle. Here's where being a regular polygon is important. Since it's a regular polygon, that means all of these arcs are also congruent, because if the chords are congruent, then the arcs are congruent that they cut off. So if I take the 360 degrees split evenly among 6 pieces, that's going to leave me 60-degree arcs all the way around this circle. So 60, 60, 60, 60, and 60. Now I'm really only interested in this one right here, because if that arc is 60, so is my central angle. So this angle in my triangle is 60 degrees. And now that I know that angle in my triangle, it's an isosceles triangle with a vertex angle of 60, which means I have 120 degrees left over, which means this is 60 and 60. Because those have to add up to 180, and these two we know are the same because it's an isosceles triangle. If I know that all the angles are 60, then that means that triangle is an equilateral triangle. So this side is 8, and this side is also 8. So I'm basically asking you to find the area of an equilateral triangle with sides that measure 8. So we're going to say the area of that triangle is 1/2 the base times the height. So it's 1/2 the base of 8 times the height, which I don't have. The height, remember, has to be drawn from the top of the triangle straight down to the base, where it will create a 90-degree angle. Well, since it's a isosceles triangle, that altitude is going to cut this into pieces of 4 and 4. So one more time, I'm going to redraw this. I'm just going to take this triangle and I'm going to look at that to help me find the height. I've got a side of 4, a right angle here, a 60-degree angle down here, a side of 8, and this angle would have to be 30 because I took that 60-degree angle and cut it in half in an isosceles triangle when I draw the altitude. So I'm looking for this height right here. Well, that's a 30, 60, 90 triangle, and on a 30, 60, 90 triangle, I know the numbers are 1 across from 30, 2 across from 90, and √3 across from the 60. So 4 times 2 would have given me 8. 4 times √3 would give me a height that is 4√3. Now I know my height, so I can put that back into my formula. So the area is going to be 1/2 the base of 8 times the height of 4√3. And when I multiply all that out, I'm going to get 16√3. Well, that's the area of just one triangle. I have 6 triangles. So the area of my polygon with a side of 8 inches is going to be 6 times each of those triangles, which measures 16√3, which would be a total of 96√3 inches squared. The cool thing about this is it's going to work no matter what shape you're using. So in the next video, I'm going to show you how to create a formula doing the exact same things we just did.